Discovery of an object from another star system passing through our solar system at remarkable velocity, named Oumuamua, Hawaiian for scout or messenger, this peculiar visitor has become the center of scientific fascination and speculation. The detection occurred when astronomers at the Hakala Observatory in Hawaii first spotted a faint point of light moving rapidly against the backdrop of fixed stars. Initial calculations revealed something extraordinary. This object wasn't following a closed orbit around our Sun, but instead was traveling on a hyperbolic trajectory that would take it back into interstellar space. Unlike familiar solar system objects, this elongated, cigar-shaped body exhibited no comet-like tail and demonstrated unexplained acceleration as it departed our vicinity. These anomalous characteristics made it impossible to classify within conventional astronomical categories, sparking debates about its true nature. Teams of astronomers worldwide scrambled to gather data during its brief passage through our cosmic neighborhood, but conventional telescopes could only reveal so much. The object's relatively small size, estimated between 100 and 1,000 meters in length, combined with its rapid transit made detailed observation extremely challenging. Now the James Webb Telescope has captured groundbreaking imagery of Oumuamua, fundamentally altering our understanding of this enigmatic traveler. The unprecedented resolution and sensitivity of this space-based observatory have finally allowed scientists to examine Oumuamua in detail that was previously impossible, revealing characteristics that have astonished even the most experienced astronomers and reigniting global interest in this cosmic wanderer. Defying conventional classification, Oumuamua's distinctive attributes set it apart from all previously documented celestial bodies. While comets typically release gas as they approach the Sun, creating distinctive tails of dust and ionized particles, Oumuamua displayed no such behavior. Astronomers trained powerful telescopes on the object, expecting to observe the telltale signs of outgassing, the release of frozen gases heated by solar radiation, yet found nothing of the sort. This absence was particularly puzzling given Oumuamua's close approach to the Sun, where temperatures should have been sufficient to trigger substantial cometary reactivity if it contained typical volatile compounds. Similarly, it defied asteroid classification through its acceleration pattern, which couldn't be explained by gravitational forces alone. Careful tracking of its trajectory revealed a slight but measurable deviation from the path predicted by solar system gravity models. This non-gravitational acceleration, while subtle, indicated some additional force was acting upon the object. Traditional asteroids, composed primarily of rock and metal, don't exhibit this kind of behavior, leaving astronomers without a satisfactory explanation within conventional frameworks. This baffling combination of characteristics fueled diverse hypotheses, from naturally occurring hydrogen icebergs to extraterrestrial technology equipped with solar sail capabilities. Some researchers proposed that Oumuamua might be composed largely of solid hydrogen, which would sublimate without producing visible outgassing, potentially explaining its unusual acceleration. Others suggested exotic compositions of nitrogen or other elements rare in our solar system. The more controversial explanations ventured into the realm of artificial construction, perhaps a defunct probe or even an active technological artifact from a distant civilization. Without definitive evidence, Oumuamua remained an unsolved cosmic riddle, until the James Webb Telescope's interventions provided new insights that would challenge all existing theories. The Webb Telescope's unprecedented revelation, as humanity's most sophisticated space observatory, the James Webb Telescope possesses unmatched infrared detection capabilities, allowing it to examine distant objects with extraordinary precision. Positioned at the L2 Lagrange point, far from Earth's atmospheric interference and thermal noise, Webb represents the pinnacle of observational astronomy. Its 6.5-meter primary mirror, composed of 18 hexagonal beryllium segments coated with gold, captures infrared light with unprecedented sensitivity, exactly what's needed to study a faint, distant object like Oumuamua. When directed toward Oumuamua, it produced the first authentic image of this interstellar visitor. The observation required precise calculations and tracking, as Oumuamua had already traveled billions of kilometers from Earth. Webb's instruments locked onto the object's predicted position and gathered photons over multiple observation sessions, combining the data to create an image that revealed details previously hidden from our view. This technical achievement, requiring coordination between international space agencies and research institutions, represents one of Webb's most challenging early targets. The imagery verified Oumuamua's elongated, asymmetrical form while revealing previously undetectable surface features indicating a long interstellar journey. High-resolution spectroscopy identified a weathered reddish surface, crisscrossed with subtle variations in texture and composition, evidence of micrometeorite impacts and cosmic ray exposure accumulated over potentially millions or billions of years. These features tell the story of an ancient object that has traveled through the void between stars, subjected to the harsh conditions of interstellar space for durations that dwarf human civilization. More astonishingly, the telescope detected organic compounds and elemental compositions entirely foreign to our solar system, suggesting origins in a dramatically different stellar environment. The spectroscopic analysis revealed complex carbon chains and molecular structures that differ significantly from those found in solar system asteroids or comets. Trace element signatures indicate formation under conditions unlike those that created objects in our own planetary system, potentially near a different class of star or during a different phase of stellar evolution than what our Sun experienced. These chemical fingerprints provide the strongest evidence yet of Oumuamua's truly alien origin, definitively confirming its interstellar nature. These findings offer glimpses into cosmic diversity and raise the possibility that Oumuamua might transport fundamental life-building components across galactic distances, potentially serving as a natural vector for panspermia, distributing biological precursors throughout the universe. The detection of organic molecules, while not evidence of life itself, demonstrates that complex carbon chemistry occurs in other star systems and can survive the harsh journey through interstellar space, preserving information about distant environments and potentially seeding chemical evolution wherever these wanderers eventually find themselves. Birth from cosmic catastrophe. Current theories propose that Oumuamua may have emerged from a catastrophic planetary disruption, possibly caused by interactions with a massive star or black hole. Computer simulations suggest that when planets venture too close to powerful gravitational sources, they don't simply fall in. Instead, they experience extreme tidal forces that can literally tear them apart. These forces differ in strength depending on distance, stretching objects along one axis while compressing them along others. The result can be elongated fragments with precisely the shape characteristics observed in Oumuamua. Such cataclysmic events could stretch and distort planetary fragments, potentially creating objects with Oumuamua's unusual characteristics. The violent separation process might also explain its unique rotational properties, as angular momentum would be redistributed during the fragmentation event. The Webb telescope's detailed imagery has revealed subtle variations in surface composition that align with this theory, different regions showing mineral signatures consistent with materials that would have formed at varying depths within a differentiated parent body. This layering effect provides compelling evidence that Oumuamua once formed part of a larger, geologically active world. If confirmed, this hypothesis transforms Oumuamua into more than a wandering object. It becomes a surviving fragment of a destroyed world, bearing physical evidence of its violent creation. The implications are profound. Each interstellar object like Oumuamua potentially represents a cosmic archaeological specimen, carrying information about planets that no longer exist. The distribution of elements across its surface tells the story of geological processes on its parent body, while isotopic ratios locked within its minerals could reveal the age and composition of its home system. The acceleration mystery. Perhaps Oumuamua's most perplexing attribute was its unexpected acceleration when leaving our Sun's influence. As it receded from the inner solar system, precise tracking revealed a subtle but unmistakable deviation from the expected trajectory. It was moving slightly faster than gravity alone would allow. This non-gravitational acceleration, while small, required an additional force acting on the object. Unlike comets propelled by outgassing, where escaping gas creates a rocket-like effect, Oumuamua showed no visible emission or coma that could account for this push. This discrepancy triggered intense debate within the scientific community. Some researchers suggested conventional explanations, perhaps extremely low-level outgassing below our detection threshold, or subtle radiation pressure effects. Others proposed more exotic hypotheses involving novel physical properties or even artificial propulsion mechanisms. The controversy intensified when Harvard astronomer Avi Loeb suggested the acceleration profile matched what would be expected from a light sail, a thin reflective sheet that captures momentum from sunlight, a technology humans themselves have developed for spacecraft like Japan's Ikaro's mission and the Planetary Society's light sail. The Webb telescope's analysis detected reflective surface materials on Oumuamua that might explain this unusual acceleration. Spectroscopic measurements revealed regions with exceptionally high albedo reflectivity, far greater than typical asteroids or comets. These highly reflective patches could potentially interact with solar radiation pressure in ways that would generate the observed acceleration. The telescope's infrared capabilities also identified temperature variations across the object's surface, consistent with different absorption and reflection properties, potentially creating subtle thrust as Oumuamua rotated through the sun's light. However, whether these materials formed naturally or represent manufactured components remains an open question requiring additional investigation. The distribution of these reflective areas appears somewhat irregular, following patterns that could be interpreted as either natural variation or intentional design. Webb's instruments detected crystalline structures within these regions that have no direct analog in known solar system materials, adding another layer to the mystery. Scientists continue analyzing these observations, applying sophisticated models to determine whether natural processes in other star systems could generate such unusual materials, or whether more exotic explanations might be required. An ancient interstellar journey. Unlike objects native to our solar system, Oumuamua is genuinely interstellar, having traveled potentially billions of years across vast cosmic distances. Its hyperbolic trajectory, entering our system at approximately 26 kilometers per second relative to the local standard of rest, conclusively demonstrates an origin beyond our solar neighborhood. This velocity, too fast for capture by the sun's gravity, ensured it would continue its journey onward after its brief solar system visit, eventually disappearing into the darkness between stars. Scientists believe it was likely expelled during the turbulent formative period of its original star system, when gravitational interactions between developing planets and their parent star could have launched it into interstellar space. During planetary system formation, complex gravitational dynamics between multiple bodies can eject substantial amounts of material. Recent observations of protoplanetary disks around young stars show this process in action. As planets form and migrate, they scatter smaller bodies, some achieving escape velocity from their home systems. Oumuamua may represent one such ejected object, cast out during the chaotic early history of a distant planetary system. Oumuamua may represent one such ejected object, cast out during the chaotic early history of a distant planetary system. Yet unlike comets or asteroids in our own system, which trace predictable paths tied to the sun's gravity, Oumuamua's interstellar trajectory made it a rare and transient visitor, an object that would only pass through our neighborhood once in perhaps a million years. Its arrival offered a fleeting but priceless opportunity to study material not native to our solar system. The challenge, of course, lay in how brief that opportunity was. Traveling at such great velocity, Oumuamua was already receding from Earth by the time its existence was confirmed, placing immense pressure on observatories and research institutions to gather data before it slipped beyond reach. This urgency led to an unprecedented coordination effort among global observatories, combining optical, infrared, and radio capabilities in a race against time. Every shred of information gleaned from this object carried profound implications, not just for astronomy but for our broader understanding of how planetary